All right, let's start. Let's do a sound check. Is the sound coming through okay? Can someone tell me if the sound is okay?
Yeah, it's good.
Thank you, appreciate it. All right, so before we start, just a reminder that, if you have any questions, right, please speak into the microphone. I won't see the chat in general. If questions of personal nature, send me an email, all right? I'll get to you after the lecture or so. All right, so what we did last time, right, was a review of probability. And the point, right, is that, I mentioned that basically, right, these concepts that we talked about last time, right, will be important when we deal with like stochastic processes, because probability, right, is the foundation of stochastic processes. Not exactly that, you will see all these concepts everywhere in stochastic process, but they show up, right, at crucial places, or they're like kind of foundational buildings, right, if you will. So we talked about inclusion exclusion formula last time, right? And the most notable problem is the hat problem, right? Or the so-called rearrangement problem in combinatorics. And so we stopped at, I guess, or we started, right, talking about conditioning, where, right, the whole idea of conditioning, right, is, I guess, one important thing about conditioning that we want to come across is the idea that, is the idea that, right, conditional thinking here. So basically, when you condition on F, you can, right, effectively view F as the new sample space, or view F as, kind of what has already happened. And this is a very powerful way of viewing things, and you'll see it a lot, like when we do future sections. But right, an example of it would be, sorry, I think an example of it, right? I think my notes are just being kind of weird. Sorry. Yeah. Okay. Right. It's the E before F problem, right? Where basically, if you keep repeating an experiment, right, until E or F happens, right? And you want to ask the probability of E happens before F, right? I mean, I guess that's sort of like the English way of saying it. But if you want to interpret this statement, right, this statement is equivalent to the probability of E condition on E union F, right? Because basically, if you repeat the experiment until E or F happens, that is the same as saying that E or F has happened, right? Condition on that. So that's conditional thinking right there. And once you phrase it in this language, then, right, the probability just follows the definition, okay? Now, we went straight to the answer here because, right, part of this is review. So I don't want to go through all the nuances. But you can think about this problem again and try to see, if you were to approach it by yourself, then what you would do, right, is I suspect a lot of people would approach this from a time dimension, right, point of view. And what they would do is they would look at what happens in the first experiment, what happens in the second experiment, third experiment, and so on. So what they would end up doing, right, is they would end up having an infinite sum, right, for this probability. And it will come up to the same answer. But this will be a much harder approach, right? And this actually highlights, right, basically what happens in this course a lot. There's not a single way to solve all the problems, but there's usually an easier way, a clever way, if you will, right, of looking at things that somehow simplify things a lot. And conditional thinking, right, is actually one of the main technique that we'll be using, right, to move forward to deal with in stochastic process. And an application, right, of this E before F concept is this question right here, right, where A and B play until one of them has 2 more points than the other. Then we well, you know, this is like a warm-up question where we talked about the probability that they will play, you know, 2n number of points. But notice right here, n can be 1, 2, 3, etc., right, all the way to infinity. Meaning, right, that again, you could try to approach this question from, you know, the angle of an infinite sum, but that will be rather, again, difficult, or, you know, let's say tedious, right? I'm not so sure if it's difficult if you can see it in the right way. But if we want to look at the probability A wins, right, then we mentioned how, right, that the probability A wins is really just the probability of you play until you see consecutive A's or consecutive B's, right? The game happens in blocks of 2, right? We mentioned that as well, right? The game happens in block of 2 just by the structure of the game. But once you realize that, right, then A wins or A or B wins, right? The game will end when we have the block of AA or BB, all right? And then A wins is exactly the probability of we seeing, right, AA before BB, right? And viewing it from that point of view, the answer is like this, right? Or, you know, concretely is that number. But once again, right, that's just basically kind of like showing how conditional thinking can be used to solve a problem. All right, so let us kind of continue with the review on, right, conditional probability, right? So I skipped this slide right here, right? We don't have time to go into it. But these are actually are some very interesting questions that I strongly, right, suggest you kind of look at and, you know, think about yourself. The answers, you know, you can look up online, right? The answers to these are well known, but they demonstrate sort of like subtle, right, things happening when you have different information. Actually, right, we just discuss this question right here, right? This is E before F. Let me just give you an answer, right? If your friend comes to a restaurant and he tells you that one of his child is a girl, right? Was probably has 2 daughters. The answer here is, of course, right? Let me see here. Sorry, I'm going blank here. Right here. Let me just address this first. Like, so the situation here is that, right, here your friend comes along to a restaurant. Here your friend goes to a restaurant, but he brings along, right, a girl who is the daughter, right? So here the answer here is 1/2. While the answer here, right, is, let me see here. You have girl, 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 boy, boy, girl, right? So the answer is 1/3. Okay. So basically the difference between this and this is whether, right, your friend brings along a girl or not, and that makes a whole difference. Again, we don't have time to go into this. I will discuss this in more details in my probability class, but this is meant to kind of show you conditional thinking actually is very subtle. All right, it's not kind of straightforward as a simple as a walk in the park. All right. So to kind of highlight this more, right? Basically, once you condition on a event, you can effectively treat this whole operation as a new world by itself, right? Basically like a probability, okay? Basically, it satisfies all the axioms of probabilities that we talked about. It's including, right, this summation rule right here. And why do we care about this? Why we care about this, right, is basically this right here. This right here is what I would call, we'll see this formula later on in this class. This is called further conditioning. All right, what does it mean? So basically, right, basically the context is that, you know, somehow you have information about F, right? F is your universe, right? You have known that F has happened, okay? You have known everything about F, right? You have knowledge about everything conditioned on F. But suddenly you have extra information. You have G, right? This G right here is the extra information. All right. So before, right, you know P of E condition on F, let's say. You know it because you know everything given F, right? And you also know, you know, EG given F. All right. But now, right, you're not satisfied with only condition on F. You want to throw in the extra step, which is condition now on F and G. All right. You want to condition on this extra piece of information that's coming in, right? Or, you know, I'm not sure, it's not really Bayesian context, but it could be, right? Or some sort of like information processing. Basically, you can call this like updating information as well, right? Information comes in, right, through time. First, you only F comes through, right? So you know how the world view is look like condition F. And then, right, G comes through. And so, you know, sorry, G comes through. And you want to update, right, all your points of view based on your new information. All right. And so here, this formula tells you that, okay, P of G condition F is also known, right? So basically everything conditioned on F is known. All right. So basically, right, to get an update, right, on a further conditioning on G, basically you can notice, right, this is actually like the old definition of conditioning. This is just like the definition, right? If you cover right the F right here, right? If you cover the F right here, you see, then it reads as P of E given G is PEG over PG, right? So now it says that, okay, then because condition F acts like a probability, the rule follows the same way, right? With the condition on F. So that's all there is. But it's very important because, like I said, right? I mean, maybe as I explain it here right now, seems very natural. But later on, when we need to do this actual update, right? This extra conditioning, you might have a hard time, right? I mean, writing down this correct formula without recognizing, right, this principle right here. Okay, that condition F is a probability. All right. Any question on this one? Okay. Now, let's talk about, right, calculating the joint probability. Or what we're getting into is the so-called multiplication principle right here. Okay. So usually, all right, what students' a favorite thing to do, even after you have taken probability, is that to take the probability of the joint, you just multiply the probabilities. All right. Of course, this is not true in general, right? When you do this, the underlying assumption is that E and F are independent, right? Or put it another way, right? What you write here is only true if, right, E and F are independent. In general, right, the whole point of us studying like stochastic process and other probabilities theory is that events don't have to be independent. So in general, right, I mean, the one thing you can do is to use inclusion-exclusion formula, all right? But in the context of, let's say, stochastic process, you don't have too much occasion to use this formula, all right? Because this structure is not that intuitive in terms of like what we'll be dealing with, the models we'll be doing in stochastic process. So this is correct, always correct, but not frequently used. What's frequently used, right, is conditioning. All right. So to calculate the joint, you can condition, okay, on one of the event, and then, as I usually say, right, this is like paying it back, right? You condition on F and then pay back the conditioning price by multiplying with the probability condition on. Okay. And why is this true? Well, this is true only because, right, it's just by definition, right? If you divide by PF right here, then PE given F is PEF over PF. So it's true by definition. However, right, this way of looking at things, again, is very powerful because sometimes, or a lot of times, what is usually or by default defined is conditional probability. Like PE given F is defined first because, let's say Markov chain, right? You have conditional probability defined first, and you have to end up finding, right, the joint probability later. Okay. So it just depends on how the model is set up. So for example, right, as I kind of show you as one of the questions right here at the beginning, right here, right? You see, this right here, right, is the joint probability, right? Or a path probability. This is usually not given, right, in the stochastic process context. But in the stochastic process context, okay, it all depends on what law, right? What law is being given. It all depends on what law, right, is being given to describe the stochastic process. But usually, right, the law that's given to describe the stochastic process is some sort of a conditional law. Basically, given the history, how does the process evolve, right? That's the natural way of how things are modeled. So therefore, right, this point of view where you relate, right, the joint or the path probability with the conditional probability, or, right, the multiplication rule here, is actually very, very important or very crucial. So let's see, right, a few examples. Right. So the example, right, that let's say about it here, right, and then I guess we'll do some problems where you see it more. So for example, right, we did the hat problem where, right, remember, right, PEIEJ, right, is 1 over n, right, times n minus 1, right? And how did we get here? So remember, right, that I said the event EI and EJ, they are not independent, right? If the ith man get the jth man's hat, then the jth man hat by definition cannot get his own hat. So these events are not independent. However, right, we can do this by commutatorics, right? PEIEJ is n minus 2 factorial over n factorial, right? Because you fix the two positions for I and j, so you have n minus 2 positions left to permute, and then write over, right, the permutations of n items. But this is a commutatorics way, right? The counting way. Now, I guess maybe a more natural way to write a lot of you is what? Well, the first person, right, EI, let's say, has a chance of getting his right hat with 1 over n, right? And then notice, right, the argument goes as follows. Condition on that information, right? Conditioned on the fact that the ith man has already got his right hat, right? Then you have n minus 1 hats left for n minus 1 people. Okay? And also, and the situation will repeat itself. So conditioned on that information, conditioned on the fact that the ith man get his right hat, then the problem reduces down to n minus 1. Therefore, the jth man, right, will get his right hat with probability 1 over n minus 1, right? Conditioned on this information, right? Notice. So that's an example, right? This is an example where we use the multiplication rule, right? Condition on some event, and then we proceed, right, on how things happen, condition on that information. Again, the danger here, right, or let's say the only thing you want to do here is that a lot of people do this casually, right? Like I said, like people just multiply things out and say, yeah, of course, that's true. But when you're asked to justify, right, on what rules, right, that you do this calculation on, or, you know, to put it bluntly, right, how do you know you're correct? A lot of people cannot justify it, right? Cannot justify it. And the danger here is, of course, right, it's not when you get it right, because when you get it right, well, fine. But when you get it wrong, right, you don't know why you get it wrong. And even more dangerously, you think that you get it right, right? So we always go back to the foundation. We have to understand this is why, where we get the answer, this is why it's correct, you know, things like that. Okay. Any question about this example? All right. So there are more examples down here, right? But I guess you can read the slides by yourself. I rather go to the problems, right? And or just do them because it's the same thing, right? You'll see more examples that way too. So right here, right? So let's give like you guys 1 minute to read this problem, and then I'll ask if there's anyone has an answer, and right, we'll proceed to discuss and show you the answer. So again, right, I mean, I guess the hint here is that this is an application of multiplication. Notice that you can still do this with combinatorics. And when I teach probability, right, I would ask students to do it both ways. But here we just want to get an answer out. So whichever way you want to is fine, right? But I guess we want to kind of do it using the multiplication rule, right? So any answer here? Any suggested answer?
Yeah, I can give one. So
Sure.
you would count up the total amount of balls. So you do 6 plus 9, and then you get 15. And there are 6 white balls. So then you do 6 over 15 times 5 over 14, because after you choose
Yeah.
the first white ball, there's one less white ball.
Correct.
And then
Correct.
you would multiply that by 9 over 13, because now you're looking for black balls. And then you do that times 8 over 12.
I think that sounds correct. Exactly. Right. And then the only thing, right, is that, you know, you should recognize that this is about conditioning and multiplication, right, principle. But yeah, good. Any question here? Okay. So let's continue. Oh, by the way, right, sorry. I haven't shown you this. This is like the, sorry. So maybe one thing I have to tell you is this is like kind of the more general, right? The general multiplication rule. Right, what I've shown you is P of E1, E2 is PE2, right? Condition on E1 times PE1, right? That's all I show you. So I've shown you 2 steps, if you will. So this is like 4 steps, right? And one thing you want to pay attention to, right, is notice the structure. E4 condition on all the ones previously, then E3 condition on previous ones, and so on, right? Again, right, this sounds intuitive and obvious when I show you, but let me show you a possible alternative version that is wrong, but you might also think that is obvious. So obvious here is a dangerous word, okay? I just want to tell you that. The one that's wrong is this. So this is wrong in general. It can be correct in some contexts, but this is wrong in general. Do you see why? It's wrong in general, right? Because basically this and that are not the same thing, okay? This is conditioned on the whole history. So this is, right, the first item would be P of E4 or E1, E2, E3, E4 divided by P of E4, E1, E2, E3, right? That's the first item. While this, right, is just P of E3, E4 over P of E3. And they don't have to be the same in general, okay? Now, as in Y, right, this is wrong in general. What you can do is you can just write out all these things right here. And you see that, right, this will cancel each other. For example, right, the next item here will be P of E1, E2, E3 over P of E1, E2, right? And you see what happens here. These two cancel. And then, right, you got P of E1, E2 over P of E1. So this cancel. And then times P of E1. So that cancel, leaving you with this, right? Now, I won't repeat for this proposed answer here, but as you can check that this does not cancel. Do you understand? So that's why it's wrong in general. But why is it so appealing, and why is it so quote unquote intuitive, right? It's so appealing and it's so intuitive is because this has a chance to be true, right? Remember I say it's wrong in general, but it has a chance to be true if you're working in a Markov context, which, right, is the stuff we're getting to in chapter 4. And, you know, for one reason or another, right, stochastic process usually are Markov. But you see, that's the whole point. Just because things are usually Markov doesn't mean you have the right to assume that things are Markov at all, right? So what is Markov? Again, this is for future materials. But Markov means that you can just ignore, you can only keep the most recent information and ignore the further history than that, right? So basically, if you know the history up to today, you only need to know today to calculate the future probability of tomorrow. Does that make sense? That's why it feels very intuitive to drop E1, E2 here. It feels very intuitive to drop E1 here, etc. But like I said, right, that's wrong in general. And for example, right, in this problem right here that we're doing, that's not true, right? This process of picking out balls, right? You see the history matters. What you have picked out of the balls, right? Always influence what you're going next. You cannot just look at the ball you picked out previously only, okay, to decide the how you're going to move forward. You need to know the entire history of what you have been picking out of the urn. Do we understand? Any question here?
Quick question. So this solution is the probability solution, right? This is not the combinatorial solution?
Correct. This is not a combinatorial solution. The combinatorial solution, you would do it by counting.
Sets?
Yep.
Okay.
Say again?
I mean, I'm assuming the combinatorial solution is using multi-sets. A combination of a finite multi.
15 choose 4, and then I think here
Choose 2, 9.
6 choose 2, and 9 choose 2, that kind of thing. Yeah.
And
yeah.
then times 1 over the number of possible ways to order the sequence.
15 over 4. Mm-hmm.
Well, I think that's not it, right? That's an unordered selection, but they want an ordered selection. So first 2 are white and the last 2 are black. So
you know what? I think you are right. So yeah. Sorry. So scrap this. Correct. Excellent suggestion. So no, right? No, you're perfectly right. And probably right even a better reason why I think multiplication approach is easier here rather than counting, because counting you have to really take that order you mentioned into account. Perfect. Yeah, very good.
okay,
So yeah, I mean, if we have time, we'll definitely go into counting, but no, right? This is not a class for that. So yeah, thanks for bringing that up. But yeah, exactly. But yeah, if you counted correctly, as you just said, taking all this into account, you will get the answer we just got. Yeah. So yep, let's look at one more example of the multiplication principle. Okay. Any suggested answer here? Or I guess I'm not so sure. Sorry, maybe this is not a multiplication principle. This is just a conditional probability question.
We could denote events S1, S2, and S3 as the probability
Mhm.
that S sub I is the ith card being spade.
Okay.
And then apply the definition of conditional probability to say we want probability of
S1 given S2, S3.
Mhm.
Okay.
And then say that's equal to probability of S1 divided by
Sorry, S1 divided by S1 is 2 S3. Yep.
Yeah.
Good.
So we know there are four suits. I think that's what it's called. So there's 13 cards in each suit. So the numerator is 1 over, wait, no, sorry, 13 over 52, right? That's the numerator.
Mm-hmm.
The denominator would be 13 times, well, 13 over 52 times 12 over 51 times 11 over 50.
Yeah, so this sounds reasonable, right? We'll have to check the answer, but I think so far what all you have said is very reasonable. And exactly right here is where we use the multiplication principle, right? Yeah. But yeah, so far all you said is very reasonable. Okay. So let's check this against the actual solution. Yep. I think hold on. I think so the denominator is correct. Conditional first oh, sorry, hold on. I think, did we write down something wrong here? Compute the probability the first card is is a spade given that the second and third are spades. So like that's correct. First card is a spade. Hold on. What did we? Oh, I guess I just named things differently. So the denominator is correct, right? One second. So let E be the event that the first card is a spade. F the event that yep. So this is correct, right? This is exactly what we meant by P of S1, S2, S3. Right. And then F is the event that the second and third are spades. I don't even know why I calculated here. So I think, sorry, let me update this, right? Because this is not what we want, right? This is P of E given F. The reason is we want to calculate first card is a spade, given that second and third. So EF is correct. Wait, hold on. I guess this is so weird, right? Why did I write this? PE given F is P. Oh no, it's correct. Sorry, what am I thinking here? PEF or PF. Hold on. So I think something is wrong with our formulation here, right? First card is a spade, given second and third are spade. Oh, you know what? We got the wrong definition, right? So P of S1 given S2, S3 will be P of E given F, right? Is PEF over PF, right? Sorry. So this is the wrong definition. So, right, what you said, the logic is all fine, but we got the definition wrong. Is that okay? So, right, so this will be 13 over 52 times 12 over 51 times 11 over 50, right, of course, here this will be, 13 over 52 times 12 over 51.
Oh, that makes sense.
Yeah, I mean, sorry, I was just following your logic and your symbol, so I got the definition messed up. But if we follow your logic, right, getting the definition correctly, then this is the answer we got, which is exactly this answer. Is that okay? So yeah, right. We do use the multiplication principle here, and I think, right, actually maybe your notation, right, is a little bit better than the one that I used, but doesn't matter. Any question here? Okay, very good. So let's continue. All right, so the next item, right, is going to be the law of total probability. So, which is an application of conditioning again. So let's talk about the law of total probability. Okay. So the law of probability, right, says this. If you have a partition of the sample space, right, what does that mean? A partition of a sample space is a set of events such that, right, basically they are mutually exclusive, right? So E1, E2, E3, right? And let's say E4 here, right? They have nothing in common. And the union, right, is the whole sample space, right? If you have such a partition, then, right, given any other event F, right? Let's say F is here, right? This is F. Right? Then to calculate F, right, you just basically sum up, right, the parts of F that is in each of the E's, right? That's clear. That's intuitive, right? So this by itself can be called the law of total probability, but that's the easy version or elementary version that, let's say, not frequently used. It's correct, right? But it's not frequently used. What will be frequently used is we'll use this, but we're gonna kind of improve on it, right? Update it by conditioning. Right now we will use the multiplication rule on each of these guys to say that, right? Now we condition on, right, EI, F condition EI, and then payback, right, P of EI. So this by itself, so this right here, right, is the multiplication rule that is most frequently used. And sorry, not multiplication rule, the law of total probability, right, that is most frequently used. And you can see that this is actually the basis of things like Chapman-Kolmogorov equation in Markov chain, things like that. Will be based on this law of total probability, okay? Now, so once again, right, why do we care, or why do we, why do we want to know about this? The reason, again, right, is that a lot of times conditioning means that you have more information, all right? Now, your education in probability may give you the impression that conditioning is actually more complicated. That may or may not be true, right? Sometimes when we have more information, then whatever we have to calculate is easier. And so here, right, to calculate F, supposedly F is a complex event, and somehow the E's are your information. Then if you can if you have that extra information, somehow the calculation of probability of F is easier. Then you break it down, right, to these cases. So you can think of it like that as well. Break it down to cases. And then, right, calculate the event that you are interested in those cases, and then return, right, the probability of the case. Then you get the original probability. All right, that's the best way I can explain it, but it'll be more clear, right, with problems. But let me pause here and see if there's a question about this law of total probability. All right, so let's look at problems. Okay, so this is right here, right, is a classical example of how the law of total probability can or must be used. It's a long problem, so I'll give you a longer time to read it. And as you read it, right, kind of pay attention on why that the law of total probability must be used here. Meaning, right, that this problem naturally require you to look at things as cases. Okay, and then I'll ask for a proposed answer. All right. Does anyone see why, right? Or how we can use the law of total probability here? Why must we do it?
Because the rainy day and the dry day are mutually exclusive.
Correct. And these are the cases, right? And you see why there are cases? Because the satellite, right, malfunctioning behaves differently on these 2 days. Sorry, on these two conditions, on these two weathers. Correct. So naturally, right? I hope math doesn't have to be complex, right? It can be very natural. Clearly, you have to look at the rainy day and not rainy day. Because on the rainy day, right, then the satellite will behave like by the way, right, we're not getting, well, when we did mention it, but this is a binomial, right, distribution of n, right? And then with probability P1. This is for functioning, right? So we're looking at like not functioning, but doesn't matter. And on the not rainy day, it's going to be binomial NP2 functioning. Do we agree? And so that's why, right, we need to look at this division right here to calculate our probability. All right. And so let's see, any question here before I show you the actual solution? All right. So, right, the actual solution, you see, exactly, right, is the event that the satellite function, right? We break it down to the rain and not rain, right? And return back the probabilities, right? So that's the law of total probability. Rain is alpha, not rain is 1 minus alpha, right? So the last part is to see what this is. If it rains, right, then it behaves, right? The whole system behaves like a binomial, right? NP1. But what are we looking at? We're looking at least k components function. So we want, right, in terms of random variable, we want this binomial to be at least k in each case. Is that okay? And so if you remember your binomial distribution, right, that would involve summing, right, everything from k to n of the probability of that happening. Sorry, this is a typo, right? This is P2. That's it, right? That's the answer. Any question here? So again, note this, right? And I have had this experience because I told you I draw this material from, you know, my probability theory class, right? My experience is when I give this question on the exam, right, the students just go all over the place with the expression, you know, mixing things up, etc. And it's easy to see where that comes from, right? Because if you just go and try to memorize this whole thing, I say it's hopeless and pointless, right? Hopeless because there are too many symbols, and pointless because, you know, if I change the question, which I say I might, you're not going to get the same, right, answer, or same, you won't even know how to modify. The way you should approach it, right, again, is by understanding where the problems come from, meaning that where the problem comes from, meaning that understand the block, right? The structure of rain, not rain, and the binomial. Because once you see that things just have to be put into blocks, then the control, right, of each of those blocks, I would argue, right, is very natural and simple. That's all I can say, right? So again, right, understanding is the point, because then I can modify the question anyhow, right? And then you can just see what the blocks are and you modify the block accordingly. If you memorize the whole formula, well, that's very noble, heroic of you, but it's useless. Is that okay? Any
Are we assuming that the weather of each day is independent of the previous, like the history of the weather?
Sure, but that's irrelevant to this question so far, because we just
Okay.
asked for tomorrow, I think, right? Just one day. I mean, if you're gonna proceed with like next several days and you want to ask about that, then sure, we want to build in that assumption, right? But right now, I think the question only talks about tomorrow, so that part is not needed. Yeah.
Okay, thank you.
Sure. Okay, let's take a look at another similar question, but now this one has A and B part. Okay. So again, I'll give you some time. And as I mentioned, the structure is similar. So I guess I will maybe see if you have any proposed answer before we talk about it, or at least proposed structure. All right, so let's look at A first, right? Can someone tell me what the structure of the question should be? And what I mean is like similar to the previous question, right? Where should we branch things out? What's the first branch for the cases? What case are we looking at?
Whether the defendant is actually guilty or innocent.
Exactly. Good. Very good. Right. So we have innocent and then guilty, right? And I think it's 0.65 here and 0.35. And you see, right, after that, then we kind of see what we're facing. What are we facing? We're facing, again, right, a binomial, right, of 12. And then, well, if the person's innocent, right, then the person is going to be both guilty or convicted, right, would probably 0.2. So it might be a bit also confusing in terms of like, you know, what the success here is, right? But as long as we keep that clear, there's no reason why we should have to be right confused, right? But and here it'll be a binomial 12. Sorry, hold on. Sorry, innocent, right? Guilty is 0.1. Sorry, so we have to, and then right, guilty, innocent meaning not convicted, right? So that's a bit confusing. So we can flip things around, if you will, but this is a not conviction. So we just have to read the language very clearly. Or, right, if we want to keep with the theme of conviction, then it's 0.8. Are we okay? But yeah, they're talking about correct decision, so we have to also interpret that.
So should we also flip the innocent to 0.9?
So again, depends on what we want, right? When I say conviction, then it's correct like this. But if you want correct decision, then you're right. Innocent is 0.9 for correct decision. Does that make sense? But I was saying I was going with conviction, so that's what I wrote is correct. Are we okay with this? So it depends on what we want, right? So that's where the challenge of the problem is too. But yeah, you're right. If we want the correct decision, then it's 0.9. Right? Is that okay?
Yeah, that sounds good.
So let's see. Yeah, let's see the actual answer, right? So notice, right? So here, right, first of all, there's a lot of total probability involved where, like, again, right, we break the person into guilty, right, or innocent, okay? But notice that here, right, I guess I keep the, so what I did is I play around with the numbers, right? Because at least 9 votes to convict. So at least 9 votes to convict. So here, with if a person is, I guess, guilty, right, then the correct decision is conviction. But if the person's innocent, then the correct decision is non-conviction. Are we okay? So I was playing around with that binomial distribution from that point of view. Now you can flip, right, the probability, but then you will have to adjust your sum according to how you flip things. Of course, right, there are different ways to do this. So I'm just showing you one way. Is that okay? Any question here? All right. I think we're almost at the time of the quiz, right? So let me show you the quiz question, and then we'll continue. We'll continue at 35. Okay. So the quiz question here will be, well, since I made a mistake in this one, let's do the number 6. Okay. So this is your quiz question. All right. Again, you just have to write down the answer, submit on the assignment on Canvas before 35. Okay. And we will resume class at 35.
Do I need to fully simplify?
You ask if you need to simplify?
Yeah, I just have it in the full form. I mean, do you want me to just?
No, no. So for answers in this class in general, simplifications are never required. Okay. In fact, keep the answers in the original form is always encouraged, and sometimes just do that. The reason if you simplify, I simplify the answer, I know that, right? But don't simplify. The reason is if you simplify, when someone read the answers, actually it's harder to understand where you come from. So do not simplify in this class.
Okay, understood. Thank you.
Sure.
对吧？得冲凉了，那你冲凉快点上。
All right, let's start again. Any question before we start? All good? All right. So let's continue with, I guess, that question, right? So yeah. So the question part B, right, is about the percentage of defendant being convicted. Okay. So to answer this question, right, notice that this is also a conditional question in disguise, or more like a Bayesian question, right? So if you want to find the probability a person is convicted, right, then you also want to know whether that person is guilty or not. Okay, so here, I guess it's the same thing, right? Sorry, I guess, no, let me take it back. It's not Bayesian in flavor, but it's exactly like this diagram, right? Still innocent, guilty, and then you're facing some kind of binomial. But right now, instead of looking at the correct decision, right, then we're looking at what I was writing before, right, in terms of conviction, right? So there, right? So you divide the person, right? You divide the cases into the person being guilty or not guilty with probably 0.65 and 0.35 each, right? But then convicted, right, under the guilty case, right, you requires 9 votes. Convicted under the non-guilty case, you also require 9 votes. So that's the difference between the two. Any question here? All right. So the last thing we want to look at, right, is the so-called law of total probability. So same thing, but now it's the conditional version. All right. So we'll have need for that as well. So let's take a look at this. So the whole point, right, is, I guess you see that the theme in this, what I've been showing you so far, is almost everything has a conditional version. And the reason why we care, why we want to know about these conditional versions, is because when you do stochastic process, right, we'll do conditioning all the time. So that's why, right? So, whoops, right here, right? The law of total probability conditional version. And so what you want to compute, right, is E given F. And so if you want to, so of course, right, this is what you want to compute. So what happens, you have to drag in some extra information, right? Same thing as, you know, if you want to calculate P of E, or P of F rather, and you drag in E, right, it's the extra information, and then you pay it back. So here, right, you want to calculate P of E given F, so you drag in G as the extra piece of information, right? But notice how, right, notice how here is E given FG, but when you pay back, you have to pay back the conditional version of G given F, right? Same thing, E given FG complement, we have to pay back the G complement given F, the conditional version, because everything, right? So this actually is a theme, right, of how F, right, is its own kind of universe, right? This is a theme of P of dot given F is a probability that I talked to you, right, in the previous slide. Right here. Right. So again, right, in terms of conditioning, right, I think as you can see, the point is conditioning can be viewed, right, as adding extra information, right? You want to know if the person's convicted or not, or convicted correctly or not, whatever, right? You want to drag in that extra information, whether a person is guilty or not. And then based on that, you can do your calculation. So sometimes when you do the conditional version, right, so that means you already have some information. You still want to add extra information for that calculation. So this conditional version will work for you. Any question here? All right, so let's see the last question, right, for the problem set. Okay, so let's look at A and B, and I will tell you right away that B here is exactly the law of total probability conditional version. B is the point. But first, right, let's look at A first, and we'll talk about what B is. Okay. Any suggestion on how to do A? Should be straightforward, but I just want to see if anyone wants to suggest an answer here. Okay, so no suggestion. All right, so let's see, right? How do you solve it, right? Is basically it's given the team leads 3-0, right? What's the problem? That's team A that leads. So of course, right, is the you know, the formulation is A leads, right? Given one team 3-0, right? Let's call this E, and this is F, right? So this is P of EF over P of F, right? Of course, right? EF, one team leads 3-0, and A leads, if the intersection of that is just A leads, right? And then divided by P of F, which is one team leads 3-0. Now, A wins, right, will probably P, so A leads first 3 games with probably PQ, right? One team that leads is either A leads or B leads, so it's that. So that's the answer to A. Right? Any question on this? All right. So now, what about B? So I want you to look at B, right? And again, B is one of those questions where it's actually challenging, but you may not be able to solve it completely. But what I want to ask you is, can you put your finger on why question B is difficult? Which part of question B is difficult? Sounds coming through okay, right? I haven't got any response so far, so make sure you can hear me talk. Anyone? Why is it that question B is difficult? Or what exactly is the part that makes B difficult?
Is it because team is random? That like arbitrary? They didn't say team A wins or team B wins.
Right. I think I heard another person, right? Well, either way, right? Hopefully that's what that you want to say to
I'm
the other
sorry.
person. Yeah. But correct. But I hear the word I think you said random or something. Be careful here, right? So the reason is in a probability class, right? Everything is random. So randomness being a difficult thing doesn't mean much. I guess maybe you're referring to A or B win being random. That's not quite correct either, right? Because again, I'm just trying to kind of clarify for you, because if you kind of use the wrong word, our mind tends to think in a different way. You're correct, right? The difficulty exactly is that, right? The team that wins is not specified, right? The word is that team, right? Not specified. But that doesn't mean that, right, it's random in any way, right? Because when you think of it, one team must win, right? Either A or B must win. There's nothing random about that or whatever, right? It's difficult, but my argument is, right, is the information correct that is not specified. And see, once you kind of see that the information is not specified, then you kind of see what we'll get into. We're getting into, right, the difficulty of lacking the information. And if you lack information, one way, right, one routine way to deal with it is add that information in and then correct for it. Meaning, right, we're dealing with conditioning, right? But let's see how that is formulated. Notice, right, this is already given. So you're already given something. So you're already in the context of given that one team leads. Understand? And then you want to add in the extra information. That's why this is going to be the law of total probability conditional version, because you want to put that extra information into a conditional probability. Are we okay? So let's see how that works. Okay, so, right, the probability that a team wins a series given that team leads to 3-0. Okay, what do? What we want to do, right, notice this is like EF, right? What you want is to add in the information of where that team is, who that team is, right? And so that's exactly the G thing that we want. And so you see, of course, you have to give back G given F. And same thing here, E, F, G complement given F. Does that make sense? So this is exactly the law of total probability conditional version. Now, I guess the notation is slightly different, but this right here exactly is what we calculate in part A. And of course, right, a similar calculation will give you the other probability, right? And now, right, let's address this part, which is kind of easy, but let's address it, right? Well, if team A has led 3-0, then, you know, what happens is we know then, right, if condition on this, then we also know that that team is team A, correct? That's the advantage of conditioning, right? And that's why we add in extra information. Because once we add in the extra information, we know what we're dealing with. But if it's team A that leads 3-0, and you want to ask the probability team A wins the series, right? Let's just clarify for you, A, right? You already know this. There are 4 games left, right? What you need for this game, for this series, is that you have to win total of 4 to win the series. But if you already win 3, right, the only chance that you lose the series is for the other team to win the remaining part. But if not this, then you win the series. So that's this expression. Do you understand? And a similar explanation goes for this. Any question here? All right, so once again, right, I just want to repeat the idea that, right, that, okay, I can understand someone trying to memorize this formula, you know, as learning the homework. But I think it's impossible to memorize this formula, right? If only because I think the P and 1 minus P seems confusing to me, right? I don't know where 1 minus P is when where P is. So notice if you put one of those letters wrong, then you got the wrong answer. So rather, right, understand the formula, understand the principle and how the principle leads things into blocks. And once you know what block you're dealing with, I would argue that, right, and then drawing out this kind of scheme, right, I would argue that it should be the case that you will not make mistake. All right, so again, proceed from formulas and understanding. Memorizing the answers is never really, right, the solution. Any question? So that would wrap up the first lecture, which is the review, right? We still do, right? Further review. Let me see here. All right. So let's see the next topic. All right. So if you want, right? I mean, we'll kind of proceed through the scheme of a probability theory class, right? First, you start out learning estimate probabilities, right? You learn rules like inclusion, exclusion, and then you learn, right, conditioning, which we have gone through. The next material will deal with random variables, right? So that's what we're dealing with right here. We're reviewing random variables and how it's relevant, let's say, to stochastic processes, right? So I guess here I just want to kind of first talk about the relevance. It should be obvious, but it's worth mentioning it, right? So a stochastic process is a family of random variables indexed by time. Saying that alone, right, is enough to say that you have to know random variables, right, before you can understand the stochastic process. All right. But you know, the notion of random variables or the types, right, or the number of random variables you have to know are a lot. I mean, or let's say there are a lot of random variables out there, right? There are things like chi-square or the t distribution, which are more relevant to a statistics class, right, rather than a stochastic process class. So we'll mention enough, right, about random variables here, especially the ones that are likely, right, to show up in stochastic process later on, okay, as a review. And so I guess here, right, I just want to mention, right, two big random variables, the Poisson and the normal, right? The reason is they are foundation, right? They're building block for Brownian motion and Poisson process. So that's why, right? I mean, at least these two, but of course there's some more. And what do you need to know about, you know, this distribution, right? You need to know them thoroughly, as in distributions, meaning the probabilities. You need to know the expectations. You need to know the variance, I guess variances, and you need to know conditional distributions involving them, right? Meaning there are a lot of information here, but we'll kind of go through enough, and then if we need something more, right, we'll build it up. Okay. Here is another example of how random variables enter, right? A stochastic process, and I think I showed you this before as well. A random walk, right, basically is a sum of ID random variables, right? These ID random variables represent the step, right? The step size, right, of the random walk. So basically, right, sum of ID random variables is an important topic, right? When we start stochastic process. So we'll mention that topic as well, right? I mean, not a particular random variables in general, but like sum of ID random variables. So I guess the theme, right, is that we study family of random variables like Poisson, Brownian motion, like Poisson and normal, and some kind of like famous, right, well-known random variables. And then, right, we'll look at sum of ID random variables as another topic. The last one is the topic of indicator function, right? Indicator random variables. All right. I forgot as I prepared this lecture, if I put everything into this one single lecture, I put in maybe lecture 3 or something. But basically, what I want to show you here is that 3 kind of main ideas we'll look at. The first one, right, you would see in a standard probability class, right? I mean, family of random variables, the well-known one. The second one you should also see in a standard probability class, but we'll probably do something that you a little more advanced, so you may not have seen it. And the last one is not mentioned too much in the probability class, which is the use of indicator function. All right, which is kind of, so that's new, and that's actually a big part of a stochastic process, especially when you deal with the Markov chain. Well, not even there, not even finishing yet, right? Conditional distribution. So we need to look at conditional distribution of random variables, meaning that, right, how to look at, let's say, x given y, that kind of thing, right? And as I mentioned here, right, conditional distribution is important because, you know, they're sort of like appear naturally in Markov chain, right, for example. And we'll look at condition. So I guess the way I say it here, right, you'll see all these ideas in this lecture. And then the next lecture or the future lecture, we'll see conditional expectation, conditional variance. So in terms of scheme, right, I think roughly speaking, we are somewhere in the territory of chapter 2 in Ross, something like that. We're in chapter 2 right now of the textbook. All right, any questions so far about the topics that we'll be going over? All right. So the common random variables we'll be looking at, right, are these ones, like Bernoulli, binomial, geometric, negative binomial, hypergeometric, and Poisson. For the discrete ones, I guess we can skip the hypergeometric. It doesn't show up as much. But for these random variables, right, you need to know their mass function, their expectation, their variance. Okay. We need to know or at least, you know, these random variables have parameters. So basically just remember that they are parameterized random variables. That's all there is. And then, right, these random variables have connection. For example, right, the geometric has a connection to negative binomial. The binomial has connection to the Poisson. The Bernoulli has connection to the binomial, right? So the connection here is important because when we deal with models and stuff like that, let's say we sum the Bernoulli, if we don't recognize the binomial, then we're missing out on, right, that link, for example, okay? So we'll mention this as well. But yeah, right, these facts right here should be memorized, as in like you should be very, very familiar with these things, right? As we move forward, we'll use this knowledge pretty casually. All right, so let's start out with the most basic one, right? The Bernoulli. The Bernoulli, right, is a random variable that takes on two values, 1 or 0, right, with probability p and 1 minus p, right? So a lot of times, right, it's just written as 1, right, and 0, right, p, 1 minus p, right? So it's as easy as that, right? But what people may not notice, right, is that the 1 or 0 here is not innocent, right? It has a role. 1, right, denotes a success. 0 denotes a failure. So when you sum up, right, a bunch of Bernoullis, actually what you're doing is you're counting the number of successes, right? If you sum up the Bernoullis, right, you think about it, if you sum, right, each of these takes on value 1 or 0, right? If you sum up a bunch of 1s or 0s, then all you're getting is a total number of 1s, correct, in the sum. And so what happens is that, right, these are related to the indicator function, meaning that they indicate whether, right, what you're looking at is a success or failure. We'll look at that more, right, in the future lecture. But right now, the Bernoulli is not just a Bernoulli, right? It has an important role of being indicator function. So expectation, right, is p, variance is 1 minus p, 1 minus p, right? Follow the formula. By the way, right, variance of a random variable in general is expectation of the squared, right, minus the squared expectation, right? I hope everyone knows that. All right. Next one is the binomial, right? And we even looked at the binomial, right, in the previous problem without even, you know, working over this slide. So let's just mention it real quick, right? A binomial, right, takes on value from 0 to n, right, where it denotes a number of successes, right, in n independent trials, right, each with success probability little p, right? And a Bernoulli, right, is a special binomial when the number of trials is 1, right? And here, if you have independent, identically distributed Bernoulli, and you sum them up, then you get a binomial, right? Because you think about it, all you're doing here is to count the total number of successes, right, in a number of independent trials, in an experiment with n independent trials. right? A binomial has expectation n times p and variance n times p1 minus p. So, right, a binomial is a generalization of a Bernoulli, right? And then we have the multinomial, which is a generalization of a binomial, right? So what is a multinomial? And the multinomial probably is something that you don't see a lot in a probability course. But, right, basically, if you look at, let's say, right, a binomial like this, right, x1 up to xn, each of them, right, has values 1 or 0, right? Which denotes whether it's success or failure, right? So basically, you think about it. So each of this is a trial, right? It's a trial. What happens is that, right, these don't have to take on only 2 values, right? Or you think about it, like an experiment doesn't have to be a success or a failure. An experiment, or sorry, a trial, right? Doesn't have to be a success or failure. A trial can take on like more than 1 value, right? It can, in particular, it can take on R values, right? But in this way, we don't really denote them as, you know, how to say this, right? As numerical values as much, but we'll look at like type, right? So each of these has R types, right? Counting from type 1, type 2, up to type R. All right, does that make sense? So, right, and here the notation can start to get a little bit tricky or, you know, confusing, right? So pay attention to all these numbers. N, right, is a number of trials, right? It's a number of trials that we conduct. But R is the number of results, right, that each trial can take. Maybe an example to clarify this, right, is that maybe blood type, right? If you have N people, right, coming in for blood check or something like that, then you can have 100 people, right, coming in for a blood check. But each of this person, right, can only take on, well, as far as I know, right, 4 blood types, right? So here N would be 100, for example, but R equals to 4, right, for blood type, something like that. Again, right, when we give like concrete example or specific example, then it's not confusing, but a lot of times we operate in, let's say, abstract context. So it's very important, right, for you to pay attention to, right, which symbol is which, okay? And so what are we interested in? What we're interested in, right, so the multinomial distribution keeps track of, right, notice this is really a vector value, random variable, right, it's vector value. Why is it vector valued? Because they have to keep track of how many K1 types that we have. Sorry, how many type 1 we have, how many type 2 we have, and how many type R we have, right? Of course, the total number of people with these types must sum up to the total number of people we have in the experiment. So again, right, in terms of the blood types, right, basically we're looking at how many people have blood type A, type B, right, type O, and type AB, right? So how many people have this? Let's say 20, 30, 25, 25. I'm just writing down some arbitrary numbers, right? But that's a possibility, right, of the number of people with these blood types when they come in and check. But, right, in general, right, you just want to keep track of how many people, how many trials, right, having this type of outcome. And the answer is what? The answer is, right, well, you know, out of N, right, total number of trials, choose, right, where this happens, right? So N choose K1, K2 up to KR. So this is the multinomial coefficient, right? Which is really N factorial over K1 factorial times K2 factorial, etc. times KR factorial, right? So this is a multinomial coefficient. And then, of course, right, you multiply with the probabilities, the corresponding probabilities of that happening, right? K1 represents the number, right, of success of type 1, so P1 to K1, K2, etc. to KR. So right here, when R equals to 2, it coincides with the binomial distribution. Notice, right, why does the binomial distribution we don't have a vector value? The reason, right, is implied, right? because we only keep track of the number of successes. But if x equals to k, right, really, then if the number of successes k, then the number of failures is n minus k. So we don't need to keep track of both of them at the same time, right? We only need to keep track of success. But, right, I mean, if you reduce the number of types to 2, then that's the binomial distribution. We'll see the multinomial distribution quite often, or at least more than once in this class, right? For example, right, you think of a Markov chain, right? If you go through different states, I mean, it's not really multinomial because these steps are not independent. But if you think, right, if you want to keep track of how many times you go through state 1, how many times you go through state 2, etc., then the flavor, right, looks a little bit like the multinomial distribution. All right, any question about this multinomial distribution? All right. So let us take a look at this. Okay, so it's a mouthful. And as you can see, we go through chapter 2 already. We go to chapter 2 already. Take a look at this, right? And there's a hint to the question. Of course, I'll show you the solution. But more often than not, what goes on in these courses, if you just chase a formula, I would say you will be super confused. All right, you will be confused, guaranteed. What you want to do is, of course, you have to be able to work with the formula, but you want to kind of step back a little bit and take a look and think about what's going on, as in like an intuitive picture. So in this case, right, with this conditioning, right, intuitively, what do you expect the answer to be? And then you can use that as a guiding thread, right, to see if the formula works out as you intuitively expected. That will be much more helpful than just chasing the formula. It'll be very, very difficult. Okay. So first of all, right, I'll give you a challenge. And if you can do this, I think you're doing okay in this class so far. Can you say in English what this means? And by English, I don't mean you telling me, oh, this is a conditional probability of blah, blah, blah. That's just reading the formula out loud. Can you interpret this statement in a meaningful way? What are we talking about here? Or if you want, right, use the blood type example I just gave you. Can you cast this in terms of the blood type example? All right. So first of all, right, I hope this is clear that that's just talk about multinomial distribution, right? That's just fancy language for multinomial distribution. Okay. So what are we given right here too, right? What we're given, right, is the number of outcomes of the R type. So in terms of the blood type example, right, you think about what happens is this, right? Suppose you have 100 people coming in, you have 4 blood types. You're given that the blood type O has, like, I don't know, let's say 22 people. Does that make sense? That's the information you're given. You're given, never mind, it's called X of R, right? It's X of whatever, it's fine. Basically, a type has that many outcomes, right? The blood type O has 22 people. Now, given that, right, what are we asking? We're asking for the remaining of the types. Is that okay? The remaining of the type. So the remaining of the types and the outcomes of that. So first of all, right, notice that it's not spelled out exactly, but what do you think the relation between the xi here and the j? What's the relationship?
Is J a defined form of, like it's a set constant that would have represented xj?
It does not represent xj. It represents xr, right? Because
Sorry.
it's a number of outcomes of R type, right? So in other words, the sum of these must be
It won't come to n.
exactly sum up to n, right? So in other words, coming back to the example of blood type 22, right? So what happens? What are we looking at? We're looking at the remaining 78 people, correct? And what we're looking at? We're looking at the distribution of the type A, type B, and type AB among those 78. Agree? That's it. That's what's going on. And if that's what's going on, then what do you think the answer intuitively will be? Let's take the blood type example first, and then we'll look at the abstract case later. If I know type O has 22, right? And then, so here, right? I mean, let's give it some concrete number. I don't know. Let's say type A has 0.22 probability, type B has 0.25, type C has 0.25, and type C, type AB, right? And let's say type O has I guess 28, right? Then given, right, that type O in the sample of 100 has 22 outcomes, right? So we have 78 people left. So what are we looking at? We're looking at, right, the distribution of AB and AB blood type in the 78 people. So intuitively, right, we're still looking at some kind of multinomial distribution. Do you see that? But the multinomial now will be what? Modified. How? First of all, right, before we do, yeah, go ahead. You want to say something?
Oh, sorry. Continue.
No, I want to hear you, right? I mean, people hear me all the time, and so that's boring. Let's hear from you.
Oh,
You
I
want to say
think
something? Yeah.
I think the only change would be that n becomes like an n prime, right? It's a reduced sample space. It's 78 rather than 100.
Yeah, but that's not it, right? There's more change.
Okay.
What else?
There's
Before,
only
how many
3
types do we
outcomes.
have? Yeah. Use the word type, right? Outcome would refer to, right? Correct. There'll be 3 types, not 4 types. Excellent, right? Because now O cannot be in there anymore, correct? But finally, the most subtle thing is, are the probabilities going to be like this?
No, right? Because
No, because they have to sum up to 1, right? And if you use the probabilities like this, they won't sum up to 1. So how do you think the probabilities would change? So you'll see, right? But intuitively, the probability will be type A will be 0.22 over that. Basically, the relative ratio of this over the sum. And same for B and AB. Does it make sense? All right. So having gone through all those, right, intuition, let's look at this actual calculation, which, by the way, right, is this, right? This is PAB over PB, right? PEF over P. Is that okay? This is E, this is F. So this is PEF over PF. Right, but let's see the simplification of that. If you divide these two out, right, notice, right? So what's going on here? What's going on here, right? If you simplify this multinomial distribution, right, you have n factorial on top, right, over, you know, x1 factorial, x2 factorial, etc., right, and j factorial. And then the bottom, you have n minus j factorial, but you also have, right, notice x1 factorial, sorry, so n choose j, right, sorry, it's n choose j. So you have n factorial, n minus j factorial, right, and j factorial. So what cancel is n factorial cancel, right? J factorial cancel, bringing n minus j factorial on top. So that's exactly this multinomial coefficient, right? And then, right, second of all, right, how do we arrive at this, right? So P, PR to the J cancel with PR to the J, right? And notice right here is where we use the fact that x1 plus x2, etc., right, plus x sub r minus 1 is equal to n minus j. So this raised to n minus j can be distributed equally to each of these terms like that. And so that's what we have. Which, right, by the way, I hope you see that this is exactly the blood type example I just told you, but now in the abstract. Any question here? All right, so part B is just the, I don't know, intuitive, right, blah, 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 is exactly what we just talked about using the specific example of blood type, right? There's no precise answer to B, right? B is just meant to tease out, you know, how you feel about this question. But all right, any question on this one? All right, so let's try to cover a few more random variables, and then we will be done for today. We won't really look at the hypergeometric, or I won't cover it because, you know, I don't think it shows up too much, but, you know, read it on the slide, right? The geometric will show up a lot. So the geometric, right, is the model, right, of basically, right, number of trials until you see the first success, right, whose success probability is P. So the picture of it, right, is something like this, right? You have a sequence of 0, right, 0, 0, 0, right, etc., and then 1, right? So this has length n, right, where this is 1 minus p, 1 minus p, right, and 1 minus p, and this is p, right? So if you want, right, you keep tossing a coin, right, a biased coin, until you see the first head. Or if you want, right, you toss the dice until you see a 6 or something, right? A number of times it takes to do that. So geometric, actually, if you note, right, in terms of time dimension, what kind of phrasing in the language of stochastic process here, you can call it some sort of like time, right? Random time. It's a stopping time, if you will. It's a time you wait until an event happens, right? Where that event has probability, right? The time here counts as discrete time, okay? And so no surprise that, right, the probability is like this, right? You need to at least have to have one trial, right, before you have a success. And this is the expectation, this is its variance. We'll talk more about this when we look at conditional distribution, right? But for now, we'll just accept this formula as correct. All right. And the negative binomial, right, is the generalization of the geometric. So if the binomial, sorry, the geometric, right, is looking for the first success, right? Then the negative binomial is looking for n successes, right? The picture will be like this: 0, 0, 1, right? And then 0, 0, 0, 0, whatever, right? 1, and then 0, 0, 1, whatever. So here, let's say n equals to 3. So I'm doing a bunch of, right, trials until I see the first 3 successes. Okay. I guess I forgot to mention, but both the geometric, right, and the negative binomial have something in common, which is the last trial, right, must be a success, right? Because you stop when you have reached that amount, right? You keep tossing a coin until you see 3 heads. I mean, not consecutively, but right, first 3 heads. You keep tossing dice until you see a first 3 5s, whatever, right? So a last one has to be a success, right? But the negative binomial, right, will require more than 1 success, right? But yeah, okay. But so how does that work in terms of probability? Notice, first of all, right, if you want n successes, then you have to have at least n trials, right? If you want 3 successes, you have to have at least 3 trials, right? This is a minimum you have to take before you have 3 successes, correct? But in general, right, what happens? In general, what happens is you know that the last one has to be success. This is fixed, right? So this is a sequence of length k, right? This is a sequence of length k. Sorry, so I should call this k, right, not n. This is a sequence of length k, right? But the last one is fixed. So the previous ones, which is k minus 1, right? Out of these, there must be n minus 1 successes, right? In this case, 2, right? Out of these, there must be 2 successes. So we choose the positions, right, of those successes. All right. The last one's fixed, so is there. And then you multiply with the probabilities of how many how many failures and how many successes, and then you get it. Right? So that's the negative binomial. There's an alternative formulation of the negative binomial. We won't go into it. Basically, you can count the number of trials to get to n successes, or you can count the number of failures until you get to n successes. Different ways of counting leads to different way of writing it and some slightly different math. But we'll stick to this because it's more intuitive. All right. There, right? So our definition has the advantage that the geometric is a negative binomial, right? When you look for only 1 success. But more importantly, if you sum up independent, identically distributed geometric, then you get a negative binomial. All right. Why? Because you look at, right, this picture right here. This right here is a geometric, right? You keep doing until you see the first success. And then you forget about it and keep doing it until you get to the second success. So that's another geometric. And then you forget about it again and you do it 1 more time. So this is the 3rd time. So you sum up 3 geometrics and you get a negative binomial, right? Why do we care about this? This right here, right, is again an example of what we call sum of IID random variable. It has the advantage that when you calculate expectation, right, expectation of the sum is a sum of expectation. But we just know that each of the geometric has expectation 1 over p, so that's n over p. Now, variance doesn't work in the same way, right? Variance of a sum is not the sum of variance, but if you have independence, then that's true. So here we also have, this is a sum of the variance, right? And we just talked about how each of the hypergeometric has this variance. So the answer is this. Notice that if you calculate using the conventional way of definition, this will be very painful. The formula will be very painful. So recognizing, right, that a random variable is a sum, or the way we say is we break down, right, the random variable into simpler random variables is a very important technique, okay, in stochastic process. Any question? All right, I think I went slightly beyond time, but above time, but all right, so let's stop here, right? And I'll see you on Friday.
Thank you.
Sure,
Thank you.
Thank you, Professor.
Yep.
Have a nice day.
Thank you, Professor.
you too.
Thank you.
Thank you. Thank you. Yep. Thank you.